Howdy all. We are Group 13 and I, Rishabh, along with Ding and Rungu, are going to present a paper on joint caching and routing in cache networks with arbitrary topology. Let's take a look at agenda first. We will start with introduction and motivation behind this paper, moving on to proposed solution or contributions. Then we will discuss the network model and the algorithm design, where we will analyze the complexities of these solutions. Finally, we will conclude with the results. I'm pretty sure we all have been frustrated at one or the other point in our life where we are all set to watch a favorite movie or exciting football match, but due to network issues, it does not load up or the stream keeps on buffering. We check the connectivity and router and wish it was blazing fast without any issues. Hence, to provide a seamless experience, it is really important to make a network reliable, faster, and cost-effective. To achieve this, we will expand on two techniques already discussed in the class, caching and routing. Giving a quick background on these two methods, caching is a technique to store frequently accessed data in a cache network close to the user. It can be an end user's machine or a cache network closer to the user like CDN, which we talked about in the lecture. Caching offers the benefits of reduced bandwidth and reduced network access time. On the other hand, routing, as we know, determines the path in a network from source to destination. There are different routing algorithms for different topologies, like we learned in the class, such as distance vector or link state routing. Routing has a significant impact on network performance. There has been plenty of research on optimizing both these technologies to achieve our goals, but I would like to propose an interesting direction, which is why don't we consider combining both these methods and then jointly optimizing it? That's what our research paper focuses on. This research paper proposes a new approach for optimizing cache networks with arbitrary topology by jointly caching and routing. It's like making a superhighway for data that allows it to reach its destination quickly and efficiently. Now coming to existing work, there has been some prior research done in this area in a variety of network scenarios like ECEN, CDN, or content provider networks. But majority of existing works focused on specific limited topologies. Example, a 3-tier hierarchical topology or a 2-tier hierarchical topology. These special topologies have very limited routing options, thus simplifying the problem. Among the works which consider the general network topology, only a few provided performance guarantees. However, they did not consider link capacity constraints, which again greatly simplifies the routing problem as it is enough to route each request to the nearest replica of the requested content. Besides caching and routing, other joint optimizations such as joint cache deployment, request routing, and content placement have been studied. But due to the high complexity of these problems, existing solutions are mostly based on heuristics. Let's see now how our paper addresses these shortcomings, most important being reducing the exponential time complexity of these existing solutions. In this work, we analyze the complexity of the problem and develop polynomial time algorithms with approximation guarantees for optimizing performance. Our proposed algorithm optimizes caching and routing jointly, and it improves network performance by reducing data access time and network bandwidth usage. With this motivation and background, I would like to hand it over to Rungu for explaining the network model.
All right, so here are the contributions that the authors claim that they had done in this paper. So 4 sections. The first one, they want to formulate the joint caching and routing problem as an optimization problem that minimizes the total routing cost under linear constraints. And then they analyze the complexity of the problem and its connection to non-NP-hard problems. And the next one is the main part. So they describe how they develop efficient algorithms that focus on the integral caching and integral routing case, as well as special cases of unlimited link capacities and binary cache capacities, and also a heuristic algorithm for the general cases that alternates between optimizing caching and routing. And after that, they evaluate the solutions against some current benchmarks and show that their algorithms can significantly improve upon existing solutions in both routing cost and congestion. So next. So first of all, they want to formulate a problem according to some abstract theories and ideas to a scientific defined problem. So they can targeting that problem and design the algorithm to solve that problem. Since they are talking about caching and routing in networks, there will be three necessary models. The first one is network model. So it's the most basic environment that they will run their algorithm. They chose to represent the cache network as a directed graph in which each node serves a catalog of content items and has a cache capable of storing a certain number of items. The links between nodes have a fixed content transfer rate. And for fulfilling all requests, they decide to focus on finding a solution that minimizes the total routing cost under specific resource constraints. And they did 2 points to achieve that. So the first one is to associate a routing cost with each link that can measure any additive performance metric. And the second one is to develop caching and routing strategies that can reduce the total routing cost given a specific cost per link. And next, as we just talked about, the cache network is represented as a directed graph. So based on that graph, caching decisions are denoted using XVI. So if an item can only be replicated entirely, XVI is either stored or not stored, so either 0 or 1. If an item can be stored in fractions, XVI, then it can be between 0 and 1. Examples of how to use these fractions, including dividing items into sub-chunks and storing linear combinations as caches. Next. And the last model we need after caching is routing. So the routing decision includes source selection and routing. Source selection can be integral or fractional, where integral source selection selects a single node and fractional source selection selects a fraction of the item. They also cover that in caching model, that if it's either 0 and 1 or from 0 to 1. Routing can also be integral or fractional, where integral routing selects a single path, and a fractional routing selects a fraction of the flow. And after setting up the environment, now they are able to formulate a very mathematical problem as they explain the problem line by line. So overall, this is an optimization problem. And as you can see in the first line, it shows that to minimize the total routing cost. And from line B to line F, they are all must-have constraints. So 1B is the link capacity, and 1C is the flow conservation. 1D is the sufficient source served request, and 1E is the selected source store request. And 1F is cache capacity. And 1G and 1H are two constraints that you need to make selections. Like for 1G, you can select either integral caching or fractional caching. And well, for 1H, you can did the similar thing. So it's clear to see there will be 4 possible output problems based on the selection in the last 2 lines. So next. And before actually talking about the algorithm, they first did a complexity analysis towards those 4 conditions we just talked about. So according to each of those 4 problems that can be generated, first one is the ICIR. So it means you select both integral caching and integral routing. And in this case, this is an NP-hard problem, as they prove that multi-commodity flow problem is IC sub-problem. And it's clear in the field of algorithm is if a sub-problem is NP-hard, like that problem will also be NP-hard. So we don't need to take care about the IR now, because IC is NP-hard, so this entire problem will be NP-hard. And the similar theory will work for ICFR. Because IC is NP-hard, we can just ignore the FR. And we can record that the ICFR is also NP-hard. And the author mentions that they did not include the FCIR case because they proved that FCIR case, FCIR case is a subcase of ICIR case, so it will be solved when solving ICIR. And the last one, FCFR, it's the most easy case because it can be solved in polynomial time using linear programming. And at the end, since 3 of the cases are NP-hard, it becomes one of their motivations. That's because for NP-hard problems, there are always some spaces for improvements. So they believe they can design some good algorithms that can compete with the current algorithm and make their own improvements. Okay. So next is the detailed algorithm design, and I will hand over to Sir. 3.
Yeah, let's take a look at the inside of their algorithm design. So how to achieve the optimization goal. So we want to optimization towards the total routing cost will be an NP hard for most cases. So how can we approach this problem with polynomial time approach? It remains as a research challenge. So we need to break down this problem, this hard problem, into 3 parts. First, we will consider 2 special cases or extreme cases with relaxation on the link capacities and the cache capacities. And then after we have proposed some solutions for this special case, we will consider the overall problem in the normal or general settings. Next. So first comes to the special case that when there is no limit for the link capacities. So the relaxation will be when each link is light loaded, we just need to request from the nearest node. So this problem can be reduced or can be transformed to route to nearest replica RNR problem. Our goal is to minimizing the cost and find the good and satisfying content placement within the network. So, but the challenge is the current methods designed for these tasks complexity is exponentially increased with the network size because it considers all possible routing paths within this network. So can we develop real polynomial time algorithm to achieve this? Next. So we have several intuitions before we design this algorithm. So the first intuition is we want to only consider the least cost path instead of the all possible paths, because what we care about is the minimum cost. So we need to care only about the least cost path. So then we can apply the conventional algorithm to find the shortest path, for example, like Dijkstra shortest path, which is very familiar to us. And the optimization goal will be as follows, where the CRNR is the total routing cost. And after we have an optimization goal indicated like this formula, then we want to know how to optimize or how to minimize this CRNR, this routing cost objective in a very efficient way. So this is a hard problem, but we decide to convert this optimization goal to a monotone and submodular one. Why we want to do this? Why we want to convert this kind of objective to another equivalent optimization goal? Because there exists polynomial time algorithm for the monotone and submodular problem. For example, the greedy algorithm, which is a very commonly used algorithm. Next. And then we comes to the third intuition. So we want to effectively approximate the optimal with guarantee with the fractional solution. Because when we get the fractional solution, what we want to do is to get an integral solution. So they replace the original FRNR with an concave one, which can achieve this. And then we comes to the fourth solution. From the fractional solution, how could we run them to the integral solution, which is the one we need in the real world application. And then they use the p-patch rounding method to achieve this. Next. For this algorithm, on this special case, we also have the theoretical guarantee. So this algorithm has a polynomial time complexity related to number of nodes, number of edges, and number of serving requests in the network, or in short, the size of the network, which is much better than the previous one. And the bound of the objective can be achieved as 1 minus 1 divided by E of the optimal solution as follows. So we have a bound. And when we comes to another special case, we do some relaxation on the cache capacity. So when each node store entire catalog or nothing, so this can be called a binary cache capacity, the routing problem can be reduced to a single source routing problem in an auxiliary graph. And our goal is to minimize the cost of serving all requests in this auxiliary graph. The challenge will be the current method is not satisfying because it has the difficulty deal with the overload of the link capacity. So can we develop a better algorithm to mitigate this issue? We have two intuitions for this special case. So the first one is the integral single source routing problem in the graph can be viewed as a minimum cost single source unsplittable flow problem. And this is a very common problem in the graph problems. So where all demands should be under the link capacity. This will be our first goal. And the second goal is the minimum cost. And we have the second intuition. So inspired by previous work, the MSUFP problem can be approached by the B criteria approximation, which are usually used for the two objectives optimization. And it will start from the splittable flow to an unsplittable one. But they couldn't handle well with the demand and the capacity. So we decided to use the linear programming to compute a splittable flow that meets all demands within the link capacity, and then we convert this splittable flow to an unsplittable one with the previous algorithm. For this algorithm, we also have the theoretical guarantee of the time complexity and the approximation results. For the time complexity to solve this MSUFP is polynomial time complex related to the number of edges, number of nodes in the graph. And the approximation results, we have two objectives. The first one is the cost, and the second one is the demand, can be bounded to the optimal one as follows respectively. So after we have introduced the two special cases that have some relaxation, so we may ask, when it comes to the general case, what can we do? When it comes to the general case, we need to make some modifications to this special case algorithm. So for content placement, which is investigated in our first special case, the algorithm is very similar, but we need to generalize our optimization goal to a general case. And for the source selection and routing, which is investigated in our second algorithm part, after we get a good content placement for X, the joint optimization algorithm can be reduced to a routing problem in the graph as the previous algorithm on second special case. But we need to note that for the special case, we use MSUFP for short for the task's name, because here the S means the single source. And in this general case, we use MMSFP or MMUFP, which means the multiple source for the general cases. So this is the modifications that we need to make. And also, this algorithm not only includes its previous algorithm, it also talks about the limitations that when transfer this MSUFP to the MMSFP, which is also an open research problem. So the overview of the whole problem or algorithm can be divided into two steps. The first is we need to maximize the objective within the cache capacity constraint to find a good placement for the caching content, which is talked about in the first special case. And then we need to solve the routing problem for MMSFP and MMUFP on the graph as the second algorithm do.
All right, so after describing the algorithm, it's time to evaluate it and see how the algorithm works and see if we can compete with some old algorithms. So for the evaluation, they prepared a simulation setting. And there are a few key points they want to mention. So first, they want an edge caching scenario. So the content is cached at locations within or near user success networks. And they use above net internet service provider topology to simulate the edge caching. And routing costs are measured by delays, and each edge node can cache items. And to implement feasibility, they make sure the passes are cycle-free for link capacities. And they decide to focus only on ICIR cases with an average over 100 Monte Carlo runs for all requests. And the last one, the trace-driven simulations in a real-world scenario is implemented that with caching and routing decisions adjustments according to demand predictions using Gaussian process regression. So next, let's see the final results. Okay, so here are 4 figures provided by the authors. So the figure 5 and figure 6, the left two one are the special cases, unlimited link capacities and binary cache capacities. So first, let's look at the figure 5. The blue one is the Arthur's algorithm 1, and the other two, the yellow and orange, are K shortest paths and shortest paths. And here it's very clear and easy to see the blue one outperforms all other algorithms because it's significantly shorter than other algorithms. So we can say the blue one obviously has a lower routing cost per request. And for the figure 6, the binary cache capacity cases, the yellow and orange ones are the Arthur's algorithm 2 with different settings when K is larger or shorter. So K equals to 1000 or 2. But in this case, it performs worse than RNR algorithm. As you can see, they have worse routing cost per request comparing to RNR. But when they sacrifice the routing cost per request, they get better congestion. So if you look at the right side of the figures, the algorithm 2, no matter if the K is larger or smaller, they both have a very, comparing to the RNR, they have a better congestion. And moving to the general cases, it's clear to see that the Arthur's algorithm performs better again. So the blue one and orange one is their algorithms in the case of ICFR and ICIR. And as you can, based on the comparison of the length of the chart, so we can say that the Arthur's algorithm outperforms the current solutions in both cost and congestion, and they converge quickly within 10 iterations. Okay, so next. After seeing the evaluation, now the authors can make some conclusions to the paper. So first, the study focused on joint caching and routing in a cache network with arbitrary topology. And their objective was to minimizing routing cost under link or cache capacity constraints. And they have characterized all the complexity of problems in the 4 different cases, as you can remember, 3 NP-hard and 1 polynomial. And polynomial time algorithms were developed that achieved guaranteed approximations in important special cases. And also, they achieved superior empirical performance in the general case. And at the end, the solution worked well in an online simulation setting when combined with reasonable demand prediction. So next. So these are our own these are our views, like based as a reader of this paper. So first is the related in-class topics. So this is very clear to see the caching and routing. They are both related to the distributed systems because in distributed system, we always use caching to store the files near the user, and we always implement the routing like to connect the nodes. And we discovered 2 weaknesses of this paper. So the first one is the more complex constraints might be present in real-world scenarios instead of only linear constraints used by the authors. And also, the paper assumes a fixed network topology, which may not be realistic in some scenarios. And we also present 3 possible future works. So the first 2 are just related to the weaknesses. So the first one is to consider more complex network topology and node placement strategies. And second one is to incorporate time-varying demands and network conditions into the optimization problem. And the last one is to investigate the trade-off between caching efficiency and storage costs in more detail. So that's all for our presentation. Thank you for watching. All right.